Section 3.3 deals with what is known as the product of quotient rules. This is another tool that allows us to compute derivative functions using shortcuts without using the limit. So let's recap what we've learned in the last two sections. In section 3.1 we learned about the power rule. The power rule says that if we have a power function like x to the n, the derivative is simply n times x to the n minus 1. Bring the n down in front and we subtract 1 from our power. Special cases of this would be that if we have any number, like 3 or 5, the derivative of a number is just 0. The derivative of a linear function, mx plus b, is just m, the slope. And here's why. If we look at y equals mx plus b, and if we draw a tangent line at any point on this graph, the tangent line will coincide with this line. In other words, if we go to any point on this line and draw a tangent line, the slope would be m. Therefore, the derivative function is identically just m. So these are a couple special cases. We also know from section 3.2 that the derivative of the exponential function is e to the x. And more generally, if we have some other exponential function, a to the x, the derivative function is the natural log of a times a to the x. And then another important tool we have is what I refer to as linearity. This is covered in section 3.1, but in essence linearity says that if you have two functions added together, and maybe the first function is multiplied by a constant c1 and the second function by a constant c2, then the derivative of the whole thing is simply the first constant times the derivative of the first function plus the second constant times the derivative of the second function. This is what I refer to as linearity. It's very important that we recognize that that's a plus sign. We'll see momentarily that this does not work for multiplication or division. So here's a simple example. The derivative of 3x to the fifth plus 5 times 2 to the x plus 3 times the fourth root of x. Linearity says that we can compute the derivative of the first expression, the second expression, and the third expression and add those results together. And also, when we compute the derivative of 3x to the fifth, we can bring the 3 out in front and just compute the derivative of x to the fifth. Likewise here, we can pull the 5 out and compute the derivative of 2 to the x. And here we can take 3 and simply multiply it by the derivative of the fourth root of x. Now for radicals, it always helps to convert them to fractional exponents, so the fourth root of x is x to the 1/4. So the derivative of x to the fifth is 5x to the fourth because x to the fifth is a power function. 2 to the x is an exponential function, so the derivative of 2 to the x is 2 to the x times the natural log of 2, and then I multiply out in front by my 5. And 3 times, if I use the power rule here, I bring 1/4 down in front and I subtract 1 from the power, which gives me x to the minus 3/4. And then 3 times 1/4 is 3/4. And 3 times 5 is 15 here. And right in the middle, I just rearrange the order of multiplication. Now what about products and quotients of functions? If we have two functions divided by one another, f of x and g of x, is the derivative of the quotient simply the quotient of the derivatives, the derivative of the top divided by the derivative of the bottom. For products, is the derivative of the product of two functions the derivative of the first function times the derivative of the second function. And in class, I've stressed the fact that that's not the case. Let's take a look at a simple example to see why. Suppose we had x e to the x and we needed to compute its derivative. Would that necessarily be the derivative of x times the derivative of e to the x? Well, we know the derivative of x is just 1 because this is a line of slope 1. And we know that the derivative of e to the x is e to the x. So could the derivative of x e to the x be simply e to the x? We can look at graphs and see that that can't possibly happen. So here's y equals x e to the x in red. If the derivative happened to be e to the x, like we showed here, if that happened to be the case, we can see that there's a problem. For example, right in here, the slope of x e to the x is about 0. So therefore, the derivative would have to cross the axis, and it clearly doesn't. Also, over here, y equals x e to the x is decreasing, which means the derivative would have to be negative or below the horizontal axis. And so this doesn't make sense. So the derivative of x e to the x can't possibly be just e to the x. And so we have two rules that help us in situations like this. We won't go through the formal proofs or through all the reasoning, but one is called the product rule and other is called the quotient rule. For the product rule, if we want to take the derivative of the product of two functions, we take the derivative of the first, multiply it by the second function, plus the first function times the derivative of the second function. So I simply will rephrase this by saying the derivative of the first function times the second function left alone, plus the first function left alone times the derivative of the second. Now the order in which you do this doesn't really matter because of the addition sign, and addition is commutative. So let's go back and take a look at x e to the x. The product rule says that we take the derivative of x and multiply it by e to the x, and then we leave the x alone and we multiply by the derivative of e to the x, which we know is e to the x. So we have the derivative of x, which is 1 times e to the x, plus x times the derivative of e to the x, and the derivative of e to the x is e to the x. Here's another example. The derivative of 2 to the x times the square root of x. We take the derivative of the first term times the second term, square root of x left alone, and then we add to that the first term, 2 to the x, times the derivative of x to the 1/2. What I've done here is I've converted the square root of x to a fractional exponent. The derivative of 2 to the x is 2 to the x times the natural log of 2 times the square root of x here. And then we have 2 to the x times the derivative of x to the 1/2, which is 1/2 x to the minus 1/2. I used the power rule. I brought down my 1/2 and I subtracted 1 from 1/2 to get minus 1/2. The quotient rule is just a little bit more complicated. Let's say we have a quotient of two functions, f of x and g of x. So we want to compute the derivative of the quotient. The quotient rule says we take the derivative of f of x, which is the numerator, times the denominator function g of x left alone, minus the numerator function left alone, f of x times the derivative of the denominator function. And then we divide that by the whole denominator function squared. Now there's different ways to sort of memorize this formula. You can do whatever works for you. I've even heard people make it sound like a square dance to keep this memorized, but whatever works for you. But it's important to realize that this is a minus sign, so the order in which you do things in the numerator makes a difference. Let's take a look at something like x over x squared plus 1. Now, we can't break this up because we can't break up a denominator, so be careful about algebra. The quotient rule says that we take the derivative of the top, so we'll take the derivative of x times the denominator function g of x left alone, so times x squared plus 1. And then we subtract from that f of x, the numerator function, which is x, times the derivative of the denominator function. And the denominator function has a derivative by the power rule, x squared would have a derivative of 2x, and then 1 is a number, so its derivative would be 0. So again, we have x squared plus 1, whose derivative is 2x. So I have the derivative of x, which is 1, times the quantity x squared plus 1, minus x times 2x. Or in other words, x squared minus 2x squared, which gives me minus x squared, and then I have a plus 1. Okay, this makes sense graphically. What I have here in red is the original function, y equals x over x squared plus 1. And here's the derivative function we just computed, minus x squared plus 1 over x squared plus 1 squared. Now notice how when the original function y has a slope of 0, the derivative graph crosses the axis. That's true here, and that's true here. The slope is 0 here. The derivative crosses the horizontal axis. Okay? In here, the function is decreasing, so the slope of the tangent line is negative everywhere. We see the derivative is below the axis, negative. Over here, we see that the function is decreasing, so the derivative is below, which is what we'd expect. Now, right in here, the function, y equals x over x squared plus 1, is increasing, so the derivative should be positive or above the axis. And also, as we move from left to right here, the slope is positive and increasing, positive and increasing, positive and increasing, but then it starts to decrease, which means that the derivative or the slope is largest right around in here, which is why we have a maximum on the derivative graph. So we can check our results using graphs. Now, a couple words of warning. You don't need to use the quotient rules or the product rule all the time. Here's a simple example. The derivative of 4e to the x. It's tempting to use the product rule here. It's tempting to say, okay, the derivative of 4 times e to the x plus 4 times the derivative of e to the x. That would certainly be valid. The derivative of 4 is 0 because 4 is a number, and then we have 4 times the derivative of e to the x, which is 4 times e to the x. So that would be valid. But you know, we can also use linearity, which would save us a couple steps. The derivative of a number times a function is a number times the derivative of the function. And since the derivative of e to the x is e to the x, the derivative of 4e to the x is 4e to the x. Notice how we get the same thing, but using the product rule, it required a little more work. Here's another example. The quotient rule. X squared plus 1 over the square root of x. Now, you could use the quotient rule here, but you could also use some algebra. X squared over the square root of x plus 1 over the square root of x. Remember, we can break up a numerator, but not a denominator. Now, x squared over the square root of x is x to the 3/2. We subtract exponents. And then 1 over the square root of x is x to the minus 1/2. Now, if we take the derivative of this whole quantity by the power rule, we bring the 3/2 down in front. We subtract 1 from 3/2, we get 1/2. By the power rule again, we bring our minus 1/2 down in front, and we subtract 1 from minus 1/2, which gives us minus 3/2. So you see, you could have used the quotient rule here, but sometimes it helps just a little bit of algebra simplification first. Okay, so here are 4 functions that I want you to work on. Each of these will require perhaps the product rule, the quotient rule, or some basic simplification. Cube root of x times 2 to the x, e to the x over x squared plus 3, 4 over x plus 3 times the 5th root of x plus 4 to the x minus 7x, e to the x plus x squared, quantity divided by the cube root of x plus the square root of x. So see what you can do with these. Don't simplify your results. I'm simply concerned that you can execute the rules in basic form.